ברוכים הבאים לכל הנוכחים. אנחנו בקולוקוויום הפקולטי לאחר הפסקה ארוכה מדי לטעמי, אבל בסדר, זה גם משהו שקורה בימים טרופים אלו. היום 4 לינואר 2021, אז קודם כל אני מקווה שהתחלנו שנה מצוינת לכולנו, או לפחות יותר טובה מ-2020, וזה גם הקולוקוויום הראשון לשנה הזאת. אריאל היא זאת שתרצה לנו עכשיו על נושא, האמת שאף פעם לא שמעתי שחומרים יכולים להיות מתוסכלים, אבל עובדה, אנחנו לומדים משהו כל יום, וזה יפה, וזה גם משהו שהקולוקוויום נועד לחשוף אותנו למושגים חדשים. אז אני רק אגיד שמעכשיו ועד סוף הסמסטר יש לנו את ההרצאה הזאת ועוד 2 בשבוע הבא ושבוע לאחר מכן. שלחתי כבר את השבוע שעבר את התוכנית, אני אשלח שוב את העדכונים בהמשך, אז אנחנו נתראה קצת יותר, בתדירות קצת יותר גבוהה החל מעכשיו עד סוף הסמסטר, ועכשיו אני מפסיק לדבר ומעביר את השרביט לאריאל. תודה רבה לך קודם כל, וקדימה, הבמה שלך.
טוב. רגע, עברית או אנגלית? כי אני חשבתי שאני צריכה לדבר באנגלית, אבל מכיוון שדיברת עכשיו בעברית, אז...
הבקשה הייתה שזה יהיה באנגלית, אני לא יודע מי בדיוק נכנס ומי לא. באופן עקרוני, הבקשה הכללית תהיה החל מהסמסטר הבא, שכל מי שיסכים להרצות זה יהיה באנגלית. אם את יכולה לעשות את זה באנגלית, עדיף. אם לא, אז בעברית.
אוקיי. So, hi everyone. I'll start in English and let's see where it leads me. I'm happy to see some faces I know around, and hi to all of you that I don't know yet. Thank you for this invitation to talk. It's always a pleasure and it's a bit exciting. Although I've been working on this stuff for quite a while, COVID has made me, hasn't given me the chance actually to present it orally. The things I'm going to talk about today. So please bear with me if some issues of flow or terminology are not that easy. I apologize in advance. So I'll start at the point where I left the faculty, actually, or some of you at least. And this is my seminar lecture of my PhD. And it's not because I'm nostalgic, it's because actually the motivation remains. And I don't know who is not muted. The motivation remains. The motivation of actually, okay, I'll try to ignore it. The motivation of actually looking at other disciplines, such as fashion in that case, looking at the way they are shaping material with such grace and ease, and then going back to our discipline, architecture, thinking of this minimal effort of sewing or actually contracting a fabric and generating complex curvature, whereas for us, when we want to do complex curvature or a shape, we have to invest so much effort, actually sometimes building the building twice, as we see here in the concrete casting. And it is the same for the materials I've been dealing with in the past decade, I can say. And this is composite material. And as you can see here in the quote, actually 40% or more of the effort, and that means energy, material, cost, labor, etc., goes into the mold or the making of the tool to make the shape. And actually, wouldn't it be wonderful if we could just, with grace, sew this envelope to our buildings. So this motivation actually led me to a materiality-based approach in my research, which focused on fabric materiality or textiles, and through that, offering alternative forming processes for focusing on architectural fiber composite. Now, the fact that I'm talking about materiality is not a chance. It's because actually in the past 10 or 15 years, we can talk about a renewed view on materiality in our discipline of architecture and design. Material has been there all the time. It's not that we haven't dealt with materials before, But there is a new position towards matter in our discipline. The generic force or the potential of matter itself is actually an expansion of the architect's tool and duty as well, because now as architects, we're not just applying material to a predetermined design, but we are using the material, we are developing the material, we are enhancing our design by materials as a methodology of design. Now, when we look at structures that we know, we have a lot of structures around us that actually do that in a way. So if you look at compression that we have in pneumatics, that is the balloon, force is applied on the material, and it's through the characteristics of the material that shape is taking, that shape is defined. Same goes with tension, as we have tensile structures. And this has been a line of, it's kind of a discipline, you can say, developed in the 60s by Otto mainly, and recurring and reappearing more and more in recent years, talking about form-active or force-active structures, that is, structures that take their shape and their structural performance through an applied external force. So as long as the membrane is not tensioned, it does not perform. Once it's tensioned, the membrane adapts to the forces that are applied on it. It is in a single stress conditions, it's fully stressed and homogeneously, and this is the performance on the structure. So we know Otto and his legacy, for example, here in the Munich Stadium, and it has been developed in recent years, also thanks to computation, to more complex situations like bending active structures, where we see where structures are kind of brought to a near failure state or a buckling state, and this is the way they take their performance to this kind of pavilions or installation, and even buildings like this one of the Soma Pavilion in 2012, where the buckling of the material actually generates the shape and the performance. This is what I have applied actually in my thesis. That is applying an external force over the fabric. This fabric is fiberglass. I'm not going to get into details, but I assume that most of you know what is composite material. So fiberglass is one of the examples. And applying a minimal effort, remember my admiration to fashion and textile in the beginning, and then we can get a large deformation, but still it is an external force that is applied over the material. So we have an external force, we have material properties. It's because that the textile is a textile and it has self-organization capacities that it actually reacts so beautifully, and we get those folds and those curves, etc. So those are the elements that were developed in my thesis, and they existed in discourse or in architectural discourse way before, and are now more and more relevant due to many factors. But what happens in nature? When you look at this flower, you see a complex shape. It's still, it's elegant, it's undulating, it's double curved. No external force is applied. The membrane is not confined. So what is the shaping mechanism of this flower or any other soft, thin membrane that undulates in nature? And this question actually has been interesting. A lot of people, mainly in the domain of physics, in the, let's say, 2 past decades. So in parallel to our new understanding as architects of materiality, there has been a parallel current in physics where also material is being understood a bit differently. Solid material has been understood differently, mainly in the domain of soft matter. So physicists started looking at all these elements in nature and asking themselves, okay, so how does element take shape? I was so excited in the beginning that I forgot to mention that this research I will be talking about is the fruit of a collaboration and now a postdoctoral fellowship at the Rakach Institute of Physics in the Hebrew University, led by Professor Eran Sharon. And actually, Eran Sharon was one of the pioneers of this domain to start and understand what are the criteria or what are the elements that make the shaping of these membranes, self-shaping, of course, of what we call thin sheets. And for that, physicists needed a theory. So in the past 2 decades, they've been looking around a lot of phenomena in nature to try to understand how this global shape is achieved actually by local active deformation of the material. We see it all around in nature. We hardly see it yet in man-made structures. What we see here, and we're going to see it again afterwards, is the nature's example of a seed pod that is actually actuated by a local active deformation of the seed pod due to swelling. And below, we can see the synthetic lab-made sample that actually operates on the same principles. So the names of soft matter, nonlinear physics, self-shaping of membranes are the names that are related to this domain of physics. And it's been proliferating in recent years. You can see most of the research here is quite contemporary. And those are examples of synthetic realization, lab realization of systems that operate the same way that we saw before, the actually active deformation, local active deformation of the material in nature to generate a shape, also called automorphing. So if before I was dealing with the material capacity or material criteria or properties of fabric and the way these could generate extraordinary forms by the application of minimal energy, now what I'm looking at in the same objective is how we could generate our material could take its shape by itself, or automorphing, as we can see the model of nature. So this is, I was just mapping the parts of my research that are related. So this is the part that deals with fabric materiality. I'm still developing the hysteretic behavior of the elements I've developed in the PhD. So this is on the left side, whereas now I'm not interested in external application of force, but what are the internal or intrinsic conditions that we could program in a way in the material for it to take shape, obviously in a controlled manner. Now comes the theory. I'll try to be really brief. I'm not a physicist or a mathematician, but these elements are important to understand the framework that these physicists or my hosts, colleagues, friends now, the language they're talking. So seeing the membranes in nature, it is quite obvious, so it's quite clear that there is a field in addition to the properties of elasticity that encodes some internal geometry of the sheet, something internal to the material, to the surface, that determines the way this surface is gonna behave once deformation or growth takes place. So actually 2 elements are part of this equation. The first property is Gaussian curvature. I'm not sure everybody is familiar with that. I'm going to try to do it very briefly. Basically, any surface that is curved can be dissected in 2 perpendicular planes, which gives us the mean curvature, or radius. And the relationship between these 2 radius that we see here actually determines the Gaussian curvature. So here we have this concave or sphere-like positive Gaussian curvature where both circles look at the same size. Here we have a saddle shape or a negative Gaussian curvature where one of them is looking to one side, let's say to the inner side, and the other radius is looking to the external side. And a 0 Gaussian curvature where we have one circle and one line, where that is one radius that is infinite or no curvature at all. So this would be a sphere, and this would be a hyperbolic paraboloid or a saddle, and this could be a cylinder, for example. Shape, as weird as it may seem, is determined by curvature. So the relationship between these two radiuses that gives us the Gaussian curvature K, so it's K1 by K multiplied by K2, this determines the shape. This agglomeration of Gaussian curvature over the surface determines shape. Now, what determines Gaussian curvature? This is the second element. Now we go to the metrics. So what is the metrics? Actually, the distances between 2 points over the surface. This is the intrinsic property of the surface. Let's say if we have an ant going over the surface, that's the distances that she would know. And here comes our little friend Gauss with the Gauss theorem. And that's where everything gets a bit complicated, because what Gauss says in his Theoria et Graecum is that these two elements, these two intrinsic properties of a surface, the metric and the curvature, are related, are interconnected forever. That is, Gaussian curvature is determined by metric, by the distances over the surface. So if, for example, we have this piece of paper, now everybody sees it's flat, right? So not really interesting. Now it's not flat. It's a cylinder or a part of a cylinder. It looks curved on one side, but actually, since we have a line section, its Gaussian curvature is 0. And that's for the reason I didn't change anything in this paper. It hasn't gone any tension or bending or compression. And that is, it stayed the same element. So for this orientation, this is the same surface. It doesn't matter its specific configuration, as long as hasn't been done any change of bending or stretching. And that's what we're going to see now. So surface is determined by metric distances and curvature. And now comes growth, for example, or shrinking or swelling. So think about the leaves that we saw, the flowers. So the moment a change gets into the system, we have a new reference metric and a new reference curvature. Sorry, this is a mistake. It's a reference curvature, should be written. So A becomes A bar and B becomes A bar. And deformation is defined by these new values of what the leaf would like to grow into. So for A to become A bar, some stretching energy should be entered, right? If it shrinks, distances are changed. And for B to become B bar, some bending energy is inserted into the system. Now, okay, we can define these stretching energy and bending energy. Don't worry, this is almost the end of the scary numbers. But what you can see here, that stretching energy and bending energy, actually together, they form the elastic energy of the system. So the form that my leaf or my surface would take actually is a combination between a competition between the two, the stretching and the bending, trying to find a kind of a energy minimum. Okay, so one would say, why not A equals A bar and B equals B bar, and we're good. So we have 0 energy. Well, the thing is, it's not always possible. It's not always possible because of Gauss theorem that links A and B, or A bar and B bar. And therefore, when it's not possible, when we have one element that is satisfied and the other one that is not satisfied, then we don't have a stress-free configuration, and we have incompatible surfaces. So when we have two elements that have to stick together and they're incompatible, and one wants to go to one direction and the other wants to go to the other direction, there is the point where we have frustration. So Daniel, this is the point for you to understand. It's like in psychology. Here comes material frustration. So these elements are encoded in the surface. These are local intrinsic properties of the surface that goes some kind of change or deformation. And at a certain point, it's not satisfied or it cannot get any rest. These are incompatible sheets. So what we see here in nature, we saw this before, that change of humidity shrinks and swells these elements of the seed pod, because of their internal organization, we're going to see it later, these elements want to go to opposite directions, and now they are incompatible. This is the point where they're not stress-free, and once they open up, energy is released. So based on this analysis, what you can see here is the scientific material on the left from the research of the lab, and an artistic application, if you like, or a demonstration that you can see here on the left. What we see is two tension membranes. You see this one is stretched to one direction, the top one, let's say the white one, and the bottom one is stretched to the other direction. They're glued together. So one of them wants to go to this direction, the other one wants to go to the other direction, and they are frustrated. The moment an incision is made in the surface, as you see here, energy is released and we get shape. This is three-dimensional shape that is formed by the bending energy that is stored in the material. So you see here the seed pods, and you can see, and we're going to see it again later on more in details, but we have an analysis of the deformations that would occur to this frustrated materials with parameters that are analyzed, the direction, the angle between the two layers, the difference between them, the different behavior of thin and thick elements, and so on. And here comes the part where we as designer enter the field. We is Shira Shoval, my partner, and myself. We did this as a collaboration with Professor Sharon. In the beginning, it was just trying to understand how we could visualize or enhance the elements, the theoretical elements that were studied in the lab in the previous years, and to give it some visualization. And we took some elements of the theory that we enhanced. The first one is this very simple equation that determines that K, you remember K is the Gaussian curvature, that is the radius or the shape in that exact location. The K of the surface is actually a multiplication of epsilon by T. Epsilon is the amount of stretching or swelling, or actually the difference between the two elements that are frustrated, and the thickness. Notice that there is no value of the material. This is absolutely independent of the type of material that we're gonna introduce into the system. And this is, for me, that was for us a groundbreaking news. And we started playing with the amount of stretching of the material to get the precise radius of curvature that we wanted. The second element, we saw this before, is orientation over this stretched surface. As you remember, there are two perpendicular sides or directions where this surface wants to contract back. So one side wants to do this and the other side wants to do this. And over the surface, we can see here, we have a rotational pattern of the same elements, and the way, the configuration that it is taking after energy is released is different according to the location over the surface. This is actually the visualization of this a bit more complicated graph that we see here. Oops. What happened? Sorry. And the last element of the theory talks about stretching dominated regime and bending dominated regime. You remember I was talking about these two energies that are competing. So the balance between the two determines the resulting shape that we're going to have eventually. And you see here the thin strips that are more helical and the wide strips that are more like spherical. And the difference between them actually is determined by, I will not get into the details, but this, what we call the thin limit or the thick limit of any system, that is, there's going to be a transition that is the result between the size of the element, or the width in that case, and its thickness. Okay, so this is also an element that we played with here. You can see these small elements that are helical. That's because they're very thin. And these elements that are not going to be helical, they would rotate on themselves if they had more material. That's because they are larger. And that's the two regimes of energy. So up to this point, it was just a visualization, actually, of theory. And then we wanted to do the next step. And this point starts actually my postdoctoral research, looking at all the synthetic systems where we had encoded surfaces. So surfaces encoded with incompatibilities, as I showed before, to generate forms. It always goes to lab materials, gels, elastomer, pneumatic elastomer, etc. All these are low stiffness, expensive material. They're not scalable, they're fragile. They're not applicable to architecture. So here comes the point where we bring all this good stuff into architecture. And for that, first of all, we have to change material. And this change of material implies quite a few things. So applying the principles of self-shaping onto architectural worlds has to deal with, first and foremost, a different material that we put into play. We're talking about different sizes and a design tool that we would need to operate, to predict, to control all of this. The two material families that I've chosen are one, fiber composites. This is actually the continuation of what you saw before, of my long-term research for shaping composite without molds, and ceramics on the other hand. So very different materials, very different Young's modulus properties, material properties, whatever, but they have one thing in common. Both of them have to go through a process of heating to some extent to get their final shape. So incompatibility in fiber composite is introduced by differential shrinkage. Epoxy materials, I didn't say that, but composites are composed by a matrix, a polymer matrix. This one would contract by 5%, let's say, after curing. And fibers, advanced fibers like fiberglass, carbon, Kevlar, etc. And those would not move, actually. They would not contract at all. So the difference that we can have between layers, this is a differential shrinkage. Here, through that, we can introduce the incompatibility or unease in the material for it to take shape. On the other hand, ceramics, we all know, we put it into a kiln, the firing process. Here, shrinkage is much more significant. We talk about 5 to 12% of shrinkage in that case. And we introduce incompatibility between the layers just by putting together two materials. So this is in view of trying to find alternative shaping processes again for those both disciplines. And this is the shaping process of the composite. You see it in real time. It's not being sped up. It's a shame that we cannot be in the same room because I would have given you the possibility to sense the material. So here we have a disc, for example. It's made of two layers of carbon fiber. It's very thin. It's 0.6 millimeters. This is too noisy. And it entered the oven flat. It goes out of the oven flat and then it gets its shape. It has two stable states in that case. I'll not get into the details why. And you see that this transition between the stable states generate a sound. And this sound means that there is a release of energy. Now, this goes against all that good students or best practice aims at doing. Best practice of fiber composites, ceramics, and any other material is to try to opt for stress-free materials, getting away, taking out all residual stresses. We don't want residual stresses to mess up in our system. Here we see another example. So here are all kinds of cases where residual stresses form in the material. It can be caused by many things, by heating, by bending, by transformation, whatever. And the idea is how to get this away, to have a balanced laminate for the composite and to have a proper ceramic arrangement with no differential shrinkage. What we say is just the opposite. We enhance internal incompatibility. We want this, we harness it to generate our shape. And the first step is to see if we can get maybe not any shape, but many shapes. And this is an example of catalog of shapes in the ceramic material. You see it's a combination of two types of ceramic with very different shrinking rate. And we can get all kinds of elements with high or very little radius of curvature, a lot of curving in the surface. And this was the interest. The idea is for it to be predictable and controlled, of course. And here you have an examples of shape versatility in the composite material. So it would look like this. These are elements that enter flat into the oven, and after 2 hours you take them out and you get the shape. Of course, it's always a combination of at least 2 layers of fibers that are not identical, and each of them wants to do something else. So these families of shape are categorized into categories here, or geometrical categories. I will not get into the details of those. Each of them is described by the A bar and the B bar elements of the surface. That is what the surface would like to do, what the curvature would like to be, what the metrics would like to be. And you remember the regimes I was talking about, if it's more stretching dominated regime or bending dominated regimes. We see here the solution or the configuration that the material will choose eventually. The surface will be either this type, for example, we see here, this is the disc I'm holding in my hand, or a saddle type. This one could not be a saddle type. Due to its shape, to its size and its thickness, it will never be a saddle shape. For it to be a saddle shape, it has to be very small, for example. So these are the material constructions. We induce incompatibility in the material, and we manage to make it self-shaping. First step is actually to align ourselves with our hosts or the theory that we're relying on, and that is to try to prove that actually what happens in our material is what's expected by theory. It sounds very, it sounds nothing. It's still taking me a lot of time. These materials, there is a reason why they're not chosen for lab materials. They're not as clean and well-behaving as the gels or the elastomers. So we have a lot of noises to take into consideration. But eventually we get very good results showing that when we increase the thickness of the material, curvature would decrease. Okay, so radius of curvature would grow. Second element, and if you remember, these are the elements that we were testing initially in the latex element or tiles. Second elements would be changing the epsilon here, or the amount of stretching of the material. And that is by different fiber angle between the layers. So you can see here, each disc would have a different radius of curvature according to the orientation of its 2 layers. And this also goes according to theory. The yellow bar is the theoretical line that this should adjust to. And finally, the bending dominated or stretching dominated regimes. Here we have the ceramic materials that is actually behaving like the curves that we were expecting. So some of them would be bending dominated and some stretching dominated. So we were saying material, and now comes scale, because we cannot remain in our samples. So this is the first test to see the effect of scaling over the elements. You see discs here that are ranging between 20 centimeters and a meter. You see the elements are curling up. I don't know why this is slowed down. I'll speed it up a bit, but this whole process takes about a minute or 2. Okay. Now what we see here is actually interesting. We actually enlarged the size, but curvature remains the same because it was not a parameter in our very simple equation. So radius remains the same, and what happens when the disk grows bigger, it just continues to close the shape. And we'll talk about it if I have some more time when we deal with scaling. Here we have a disk of the same size, but this time with increased thickness, scaled thickness. So shape would remain the same as we had before, but radius of curvature would differ. Okay, so another issue that we are dealing with is gravity. Gravity was abstracted in all researches so far. It dealt with pure elastic energy. As we saw, it was the answer, or actually the solution of bending and elastic energy. When we increase size beyond a certain point, gravity has to be taken into consideration, and the effect of gravity is what we are researching now. You can see here the difference between scaled thickness and non-scaled thickness and how gravity affects the section of these elements. Now, we're not going to do chips all day as designers or architects. And the next step is to see how all this information could be agglomerated or to be used to generate a complex shape or a panel if we're architects. So what we see here is actually a panel and a baby panel, which are made by the same principles. So you see that shape is scaled up. And this was according to a preliminary design. And here comes the design tool, because of course, as designers, we cannot have a field of tensors and equations. We need to have some kind of design tool. It relies on grasshopper kangaroo elements. It's very simple in a way. Well, interface could be improved. The design is done schematically with these rectangles that you saw in different colors, initiating fiber orientation. This is kind of an internal symbol for us. And once simulation is getting started, you can see the deformation of the panel according to the input of local incompatibility, that is the direction of the fiber, and that is given here by colors. So with this tool, basically, we could design a surface to do some kind of reverse engineering to design a surface according to our need. Complex double curved surface. It's been discretized to sub-elements that each of them is relatively of simple curvature, but the overall interaction of the surface is a complex double curved one. So the process that I'm doing in my research is actually the introduction of new materials, ceramics and FRP, into the environment of the lab. As we said, it's larger, it's bigger, it's dirtier, it's not as precise, and this is the challenge in itself. First step was to prove the compatibility of what we're doing with these new material to the theory that was already acquired. Now we're dealing with gravity that was not relevant up to this point because no research dealt with these elements of such a size. And as an architect in the lab, my interest, of course, is to take it to the design or architectural world, and the design interface is an issue in itself. We're now starting to investigate more deeply the reliability of the grasshopper simulation, what points of failure we have in the grasshopper simulation, where would we need to incorporate physics engine simulation that are used in the lab, and so on and so forth. Now we get again to this final slide. Thank you very much for your time and attention, and I hope it was clear enough in English.
Thank you very much.
Thank you very much. תודה רבה. שאלות, questions?
How far away is it going to be from architecture applications?
How far?
Or maybe how close are you to architecture?
Oh no, as you know, even if it's exciting, it's always far away for two reasons. First, because architectural application needs a huge amount of adaptation to adjacent systems. So this whole interface between the elements that we would do and other elements of the building is an issue, not talking about all this other gray side of regulations and laws, etc. I'm not even talking about this. But I think the more interesting answer is that it's far away because this would require a change, a shift in the way we think about our elements or buildings. For example, the issue of control, the issue of tolerance, all these are elements that we are more and more orienting ourselves toward complete control and total and zero tolerance. These systems, they could get to complete control, but that's probably the point where they would lose their interest. If we reduce that much the degree of freedom of the system to configure itself. So I think the answer is combined by both elements, a more practical and a more philosophical one. But we are very close to getting the shapes that we predicted. So this is the first step. Now, for example, for us to get the shape that we predicted, we had some kind of castrate our surface in a way, or our system, that is to reduce or take out some options of the system to form itself. Because every given intrinsic geometry could be configured in different geometrical configuration because there are different solutions for the elastic energy that we talked about. For us to predict exactly what would happen, we had to take away some of the options, reduce some layers, for example, reduce the complexity of the system for the sake of control. So I think this is the balance.
Thank you.
And can I ask also about this? How do you know the shape is at its final stage? It will not change anymore.
The shape is the result of the deformation that the surface is going. And this deformation is due to the material process that is going on. For example, curing of composite material or firing of clay. At a certain point, clay is cold, concrete is cast, and material is cured. However, there are elements that have different stable states, like this one. Okay, this is the most simple elements that you can imagine. It's two layers of carbon. By the way, carbon and fiberglass, very different materials. They look exactly the same. I don't know if you can see, but as long as they have same thickness, the radius is going to be the same, and same shrinkage, sorry. Now, it has two stable states, right? This is a mechanical stable states, and this one too. Both of them are solutions of the system. If we don't do anything, transition between solutions or local optimum of energy is possible. And this is where it gets interesting, because this is the key to have very intelligent, low energy dynamic structures in architecture. Because if we want to deform a surface that is not meant to be deformed, we have to invest a lot of energy. While this one, because these are two minimal energy of the system, their transition is like a bump. It's nothing. And eventually one day we could program a surface that would have different stable states that we know beforehand, that we predict, that we entered flat into the oven, we get them shaped, and we can induce the change between stages very easily. I don't know if my science fiction was clear enough and you could follow this.
Yes, thank you.
I have a question. Hi, Ariel. Thank you for the presentation. Very nice. I'm very excited to see what you're doing in the postdoc. I have two questions. So first of all, you did you know how much I love catalogs, and you did a wonderful catalog of the way the form modifies. But I have two questions in relation to that. One is, you didn't talk about the form itself. I mean, you're showing us a round circle of something that clicks, but you didn't say why it's round and not a rectangular. What were the consideration of choosing all the forms the same as what we see here? These forms, I know, I understood that the form has some meaning, but not really change the way the surface, the material behave. But I think it's interesting to hear more about the connection to the form. Do you want me to wait for the second one?
Yes, actually, I have a very small brain. So basically, the reason the circle were chosen to so many samples is a fact that we call boundary condition. You see the angles of this surface. This surface is almost flat here, but very, very curved around here, because there is a special condition that is going in the boundary, and that is the angles. It's here accentuated with a 45 degrees direction of the fibers. I don't know if you can see, that makes it curve in that direction. But we try to avoid in the samples that we do for the scientific research, we try to avoid these boundary conditions, which are kind of noise, boundary effects, sorry, that is just kind of noise. And that's why it's very boring circles for this scientific boring experiments of measurements. However, this is the beginning of talking about shape. That is how we can agglomerate these elements together to get something that is more like an architectural shape, architectural in the fact that is basically rotating around the kind of middle surface. It would not be completely like a sphere. We don't talk about radius of curvature that are too small on one hand. And on the other hand, how can we get local artifacts? Maybe I'll switch to the more expressive catalog, not this one, but this one, where you can see a proliferation of shapes. These are actually mechanisms. These are more like systems or elements that we could then incorporate in a large architectural shape. For example, this, it looks very simple, but it's a complete rotation of the surface. It changes direction. So this is something that we can afterwards use. This is in the composite and in the ceramics. For example, we see that. So we have two radius of curvature in the ceramics. We would opt for longer elements. But ideally, when you talk about the theory itself, shape is just important for this transition that I showed before between bending dominated regime and stretching dominated regime. I don't want to get too much into the details of the equations because I think I'm going to be left alone here in the room. So did I answer your question? I'm not sure.
Yeah. I think, well, basically you said that's going to be the architectural part of your research, and you explain why it's different and what's the differences, which is what I wanted to hear. And the second question, it has to do with with your answer also, is that I understand that you use mainly anisotropic surfaces, and I wonder if you're also going to use isotropic surfaces. But I see here some surfaces with cut, but some surfaces that are not glued all the time, and creating all kind of interesting effects, which maybe go beyond totally glued two surfaces, something which is more, I would say, programmed, rather than just the material is one piece.
Okay, so two parts for this answer. First, all the ceramics is isotropic material. That is, there is no directionality, not at this level at least, of the material. It's isotropic material, but it has difference in section. Since you love catalogs, I'm gonna take a minute to explain this. So you see here, it's written non-compatible shapes and NEP, which is non-Euclidean plates. So NEP and non-compatible shells are two different cases of frustrated materials. The non-Euclidean plates are symmetrical in their composition, and the non-compatible shells are not symmetrical. So here we have a non-compatible shell because this one, the white, is different than the brown, and then that's where we have a difference. Now, isotropy, it depends if you talk about the surface or if you talk about the whole element. In the surface, they are not isotropic. It's anisotropic, as you see here, for example, orientation of the fibers. And it has to be different from the second layer beyond it, for it to be frustrated. Now, the point where these two elements would not be glued, it's not because of incompatibility. It will have to be programmed in advance. I'm not sure I understood how this is the element that would generate the variations, but maybe we should have a talk about it at some kind of close occasion for me to understand it. But basically, it's all actually configurations of few numbers of layers. It depends, 2 minimum, 3 or more to get the differences within the material. And this is completely encoded. Okay, so for example, one thing that I haven't talked about is you see that this one is black and brown, which is carbon and glass. So the differential behavior is also due to the shrinkage of the material that is different between the layer and the orientation. And this is programmed, this is expected. Okay, the amount of curvature and the place it's going to take and the location. And it's scalable. So.
Thank you.
Thank you.
עוד שאלות? אני לצערי מסתכל על השעון ורואה שכמעט 3:30, 3:25, אז אני מציע, אני יכול להציע שאלה אחרונה, אריאל?
בוודאי, לי יש זמן.
וזה אם את יכולה להגיד מילה על השיתוף פעולה עם פיזיקאים, או בכלל, עם עולמות אחרים.
אתה תצטרך להזמין אותי לקולוקוויום שלם על זה.
יאללה, קבענו.
No, actually, this is the thing I've learned the most in the past year. The first step, that's why I actually showed it, the latex tiles that we did together with Shira Shoval and Eran was done prior to my postdoctoral fellowship in the physics lab. And it was a collaboration. Now, it's a very different thing to do an artistic or designer scientific collaboration, which is not always easy, but it has challenges in itself, but it's one level. Another level is to go into the physics lab and try to talk their language. And this is not at all evident. And we have different ways of thinking about things, different timescales of things. I'm going to tell you a little anecdote that I had lately, last week actually. So we were researching this effect of gravity over scaling up, and we compared two sets of elements. One of them was growing disk with 2 layers, all of them, and the other one growing disk with scaled number of layers. And the analysis showed, and I did an analysis in Grasshopper of the variation of curvature along a section of a single section, and we saw a variation as we expected, but we saw kind of peaks, very weird peaks that were not expected by the theory. But all of them really were aligned in the same place proportionally in the disks. In a way so clean that I have never seen any experiment of mine up till now. So I was calling Eureka, going to Eran, telling him, listen, there is something here, everything aligns, finally my material behaves properly, like something, we don't know what, but like some things. And the first thing Eran said is, this is an artifact. Something with the tool that you're checking with is not appropriate for what you're looking. And it was Grasshopper, and Grasshopper in some sense is a black box, so we couldn't analyze some things. And I think this difference shows everything. It shows that I have still everything to learn, that I have to learn to use the other tools. And I've been breaking my brain and teeth with MATLAB in the past month. And it's not so easy at this point of my life. And there is a scientific rigor that is very difficult to align with, but highly inspiring. on the other hand. So I think that it's the most promising channel of research for me is this interdependence and relationship between science and design or architecture. It's not at all to be taken for granted. I mean, there should be invested efforts, know-how, and a lot of goodwill between the two sides, because it's very different languages. I am very, very lucky because Eran, the professor I'm working with, he is a designer in his heart, and he has high estimation for architecture and design, and it wouldn't have been possible in another configuration because it requires a lot of open mind and understanding, but the benefits are incredible.
יפה מאוד.
I hope that...
בנימה אופטימית זו, אני מודה לך מאוד, אריאל, מודה לכל המשתתפים.
תודה לכם על השאלות המעולות.
תודה רבה, אריאל.
אנחנו ניפגש שבוע הבא. תודה לכולם.
תודה רבה.
להתראות.